Hello, everyone. My name is Benjamin Rydas. I'm a PhD student at UIUC. In this talk, I'll present our work, DeepMC, which works on understanding and detecting deep memory persistency bugs in NVM programs. This work was done with help from my advisor, Professor Jian Huang. Non-volatile memory is a promising technology that has seen increasing adoption recently. It is desired for its data durability and near DRAM performance. It also offers a byte addressable interface, unlike the block interface of traditional storage devices. Despite the numerous benefits of using NVM, programming it properly is not easy. This is because it sits directly below the processor caches, and as data is flushed from the processor caches into NVM, we need to ensure crash consistency. Since modern processors use out-of-order execution, ensuring crash consistency is made more challenging, as writes may be persisted out of the program order. This results in a trade-off between the ability to reorder and issue concurrent memory operations for performance and the guarantees made about which writes are persistent. Reasoning about these trade-offs is a considerable challenge. For this reason, the community has developed 3 memory persistency models to help reason about these trade-offs. The first model is strict persistency, which requires that writes must be persisted in program order. To implement this, programmers must use cache line write-back instructions and memory fence instructions to ensure that writes are flushed from the volatile caches to NVM and that future memory operations are ordered after the current one. This offers the strongest persistency guarantees, but the lowest performance. The next model is epoch persistency, which uses the concept of an epoch. Writes in the same epoch can be issued concurrently, and barriers are only enforced between consecutive epochs. This increases parallelism and therefore performance, but relaxes the persistency guarantees. Finally, we have strand persistency, which uses the concept of a strand. Writes from different strands can be issued concurrently. That means that if we want to order 2 writes, we must place them in the same strand and place a barrier explicitly between them. This offers the highest degree of parallelism and performance, but the lowest in terms of persistency guarantees. We'll go through each with an example, starting with strict persistency. We have a simple example with 3 memory operations, A, B, and C, where A and C have a dependency such that A must be persisted before C could be issued. Under strict persistency, there must be a barrier between every operation, so we add a cache line write-back and M fence. This means that A must be persisted before B can be issued, and B will be persisted before C can be issued. This creates a false dependency between B and A and C and B that is not necessary by program correctness. This offers the strongest persistency guarantees, and it's very easy to reason about and program. But the introduction of false dependencies reduces the overall performance. Let's look at the same example with epoch persistency. We add epoch boundaries to put A and B into one epoch and C into another. Since C is in a different epoch, it must wait for A and B to be persisted before C could be issued. But since A and B are within the same epoch, they can be issued concurrently. This removes the previous false dependence between B and A that we saw, but keeps the one between C and B. This relaxes our persistency guarantees, but enables higher concurrency for an overall increase in performance. Finally, we have strand persistency. In strand persistency, we add strand boundaries to put B into one strand and A and C into another strand. In order to order A and C to maintain program correctness, we need to add a barrier operation between the 2. But since B is in a different strand, there will be no false dependencies between B and A or C. This offers the highest possible performance, but is very difficult to program and reason about correctly as the complexity of the program increases. We have discussed the 3 persistency models. Let us now discuss how programmers can use them to implement their programs. A developer could choose any one of the models depending on the needs of their program. If persistency is important, then strict persistency may be best. However, if performance is more important, epoch or strand persistency may be a better fit for the developer. While the models guide the programmer in developing their programs, programmers may not be certain that their programs correctly follow the model specifications. To better understand the challenges programmers face when developing persistent programs, we conduct a study of persistency bugs in NVM programs. In order to conduct the study, we select programs from open source frameworks PMDK, PMFS, and NVM Direct. We manually study 19 representative persistency bugs from programs in these frameworks. The bugs can occur in the example programs or in the libraries themselves. When we categorize the bugs, we discover two categories can be used to classify them. The first are persistency model violations, or that we term deep memory persistency bugs in the paper. This is when the implementation the developer implements does not follow the model specifications exactly. The second category are performance bugs, which do not influence correctness, instead only affecting the performance of the program. In our study, 47% of the bugs are model violations and the rest are performance related. Let's go over some examples within each of these categories. For persistency model violations, we could have semantic mismatch when the implementation of the program does not follow the model specifications exactly. We could have unflushed or unlogged writes. Persistency models specify exactly when items should be persisted. Therefore, if we do not have a corresponding flush to actually persist the item, then we do not follow the model specifications. We could also have a missing persist barrier. Again, persistency models dictate in what order writes should be persisted. If we do not have a barrier to enforce this ordering, then we do not follow the model specifications. For performance bugs, we could be flushing unmodified data. This results in cache line flushes that are not necessary, increasing traffic to NVM and reducing performance. We could have redundant writebacks of data, where we flush the same item twice to NVM. This again adds traffic to NVM and reduces overall performance. Finally, we could have durable transactions without updates, where we create persistent transactions that force memory orderings without having writes that we need to order. We will go through examples of the model violation bugs first. Here I have an example of a semantic mismatch using a code snippet from the hash map implementation in PMDK that uses strict persistency. This function is creating buckets during the hash map's initialization. On line 3, we initialize the number of buckets and persist that object on line 6. Under strict persistency, writes must be persisted in program order, meaning that the persist of the end buckets variable must happen immediately after line 3. Even worse, since end buckets is used on the persisted object on line 4, we have used the variable without persisting it, meaning that upon recovery, we would have an inconsistency. Next, let's discuss the unflushed or unlogged writes. Here we use another example from PMDK, but this implements the B tree map using epoch persistency. The entire function is executed within a transaction as we create a split node for the B tree map. Note that the items field of the node object is modified here, but there is no corresponding logging of this change in the transaction. Therefore, when the transaction ends and the item should be persisted, it will not be flushed to NVM and the model has been violated. Finally, let's discuss an example of a missing persist barrier. Here we have an example from the Oracle's NVM Direct framework that uses strict persistency. We're using the NVM create region. This function creates an NVM region for later allocating persistent objects. Here, we flush the region variable on line 4, but we don't have a barrier that enforces the ordering. Therefore, the writes may not be persisted in program order as future writes may be persisted before the region object, violating strict persistency. By analyzing the common trends of model violation bugs and the specifications of each model, we develop a set of rules that programmers can use to ensure that they do not have model violation bugs. For example, if a developer wants to implement strict persistency, every write should be followed by a flush, and every flush should be preceded by a single write. If a developer is implementing epoch persistency, some examples for rules would include every epoch must be followed by a flush, and consecutive or nested barriers must have consecutive or nested epochs must have barriers between them. Finally, remember that writes from different strands are issued concurrently. Therefore, if we implement strand persistency, different strands should write to different addresses. Now that we've discussed examples of persistency model violations and some of the checking rules developers can follow, let's do the same for performance bugs. First, we discussed an example of flushing unmodified data. Here we have an example from PMDK where we are initializing a task construct object. On line 5, we persist the object T, where on line 4, we updated the proto field of object T. However, the object has more fields and we are flushing the entire object instead of just the field that we have modified. This increases the amount of data that is being flushed to NVM and hurts our performance. Second, let's look at the redundant writebacks of data. Here we have a function from NVM free where we free a persistent object from the NVM direct framework. On line 3, the NVM free callback function calls NVM free BLK. At the end of this function, we have a flush of the NVB object, which is again flushed after the function returns and on line 4. Flushing this item twice in a row does not help our correctness and only hurts our performance as we add extra data to NVM. Finally, let's discuss a transaction without updates. Here we have a persistent memory implementation of invaders from PMDK's example programs. On line 12, we persist the alien object. However, if the condition that is on line 8 is not true, then the object will not be modified. Therefore, we have a persistent transaction that does not have a write in it, which unnecessarily enforces memory orderings, reducing our overall performance. Again, we take the examples of performance bugs and transfer them into checking rules that developers can use in order to avoid these types of bugs in their programs. First, if a developer wants to avoid flushing unmodified data, then every flush should have a preceding write. To avoid redundant writebacks of updated data, then consecutive flushes should not flush the same address. Finally, to avoid durable transactions without updates, every transaction should contain at least one write. We have now finished our classification of persistency bugs based on our study and discussed what rules programmers should follow to make sure they implement the models properly. To help developers detect the persistency bugs, we developed DeepMC to be able to detect performance bugs and model violations, regardless of which models developers choose. Since performance checking rules and strict persistency rules require matching writes with their corresponding flushes, DeepMC develops a static checker to track persistent objects and persistent operations and check that all rules are being followed. However, some rules, such as checking dependencies between epochs or strands, requires runtime information. Therefore, we develop a dynamic component to check those rules. Together, they can check all of the proposed rules that we developed based on our bug study. Let's first discuss the static component in detail. The first step is to compile the NVM program using LLVM into the intermediate representation. The programmer must specify the persistency model they are intending to use in this step so DeepMC can apply the correct set of checking rules. This is the only input that is required from the programmer in order to apply DeepMC to their program. In order to apply the checking rules to persistent objects, we must first understand which objects reside in NVM and when they are updated. To that end, we modify data structure analysis to extend it to persistent objects. Data structure analysis happens in 3 phases and creates an alias analysis that is context and field sensitive. In the first phase, local analysis, a graph is created for each function where nodes are created for function calls and variables with edges if one object points to another. In the second phase, bottom-up analysis, we use call-lee information to resolve the effects function calls have on the local variables in our function. Finally, top-down analysis incorporates the caller information to finish the graph. We will go through how we create the data structure graph in DeepMC. To do so, we will use an example from NVM's NVM Direct framework, their implementation of a persistent lock, in particular, their locking function itself. The data structure graph will be on the right. First, for the function call itself, we add a node for the function call and all of its arguments. On line 2, we see that mutex and omutex alias, therefore we can update the node accordingly. On the function called the NVM add lockup, we can add the corresponding node and for its return value. On the function call for NVM persist, we can add a node for that and update the corresponding arguments that are used in their function calls. This will be the result of the data structure graph at the end of phase 1. For phase 2, we will use information from the function calls in order to update their effects on our local variables here. The first function call will be NVM add lockup. We see that the return value, LK, is allocated from persistent memory. Therefore, we can mark the object as a persistent object. We also see that the mutex variable here is a field of LK, and we can update the nodes accordingly. We then use the NVM persist function call and see that it does not allocate any objects. Therefore, it will not add any nodes here. So this will be what the graph looks like at the end of phase 2. For the phase 3 top-down analysis, we incorporate the information about the arguments of NVM lock, the caller information. We realize that mutex/omutex are allocated from persistent memory. However, EXCL and timeout are not, so they can be safely removed. In the end, we have a graph of the alias analysis for all persistent objects and annotations on where and when they are modified or referred to. This will be critical for applying our checking rules. Now that we have discussed how to identify and track persistent operations in the program, let us discuss how we combine these checking rules to create our static checker. To apply our checking rules, we need to break the program down into smaller, more usable traces. To do so, we first traverse the control flow graph in depth first order. At call sites, we merge the traces into one larger trace. Since our checking rules check around flushes and fences for writes, the most natural point to split this trace is at each persist barrier. We then split the trace into smaller traces at these split points that can be checked independent, where the rules can be applied independently to each trace and checked. Note that the trace only contains persistent operations as dictated by the data structure graph. To see how we convert a function into a trace, let's use the example from NVM lock again. On line 4, we have a write to the state object and a corresponding flush and fence on line 5. Line 7 updates the mutex object, and line 7 flushes and fences it. We have a write on line 9 to LK, another write to LK on line 10, and line 11 persists and flushes. We have our split points at each of the barriers. Now let's see how we apply our checking rules to the split traces. Since this is implemented using strict persistency, we will use the corresponding model violation rules. First, every write needs to be followed by a flush, and second, every flush must be preceded by a single write. We also have the performance rules. We should not be flushing unmodified data, we should not have redundant flushes, and we should not have updates without transactions. So let's see how we apply that to our first trace. Every write is followed by a flush. The write on line 4 has a corresponding flush on line 5. Every flush is preceded by a single write, where the flush on line 5 has a write on line 4. Every flush has a preceding write. Again, we are not flushing unmodified data. We do not have redundant flushes, as we only have one flush in the trace. And every transaction should have at least write. The existence of the write on line 4 makes this correct. So we find no issues in the first trace. It is easy to see that the second trace will have the same result, as it has the exact same structure. So let's check the third trace. We immediately see a violation of the first rule. We have a write that is not followed by a flush. We also see that a flush is preceded by more than a single write. Therefore, note that the performance rules are not violated here. Therefore, DeepMC will report a warning that the write on line 9 is a violation of strict persistency. Now that we have discussed static analysis, let's discuss how dynamic analysis is done in DeepMC. Remember that epoch and strand persistency relax the persistency guarantees for higher performance. However, this relaxed execution can result in data races when the same address is updated in concurrent epochs or strands. To catch these violations, we need to use dynamic analysis. However, traditional dynamic analysis can suffer from high overhead. We use two optimizations to reduce this in DeepMC. The first optimization is that we use the data structure graph to make sure we only track persistent objects. The second is that we can reuse existing library annotations. For example, the epoch and strand boundaries indicate that persistent objects can or will be modified. And if we are not in a strand or epoch boundary, we know that they will not be modified. We show this with an example. We begin tracking after the epoch annotations. To track the updates, we introduce a shadow memory where we record accesses to the objects and use that tracking to detect when violations occur. As we traverse the first epoch, we see that X, Y, and Z are updated. The second epoch updates W, V, U, and uses X. We then stop tracking at the end epoch boundaries. We can then see that both concurrent epochs, 1 and 2, touch the variable X, which means that there's a data race to X that needs to be ordered. DeepMC will report this as a warning. We add dynamic analysis now to see the full picture of DeepMC. We implement the static analysis component of DeepMC with 13,000 lines of code on top of LLVM and Clang. And dynamic analysis is implemented using 450 lines of code on top of Thread Sanitizer. To test DeepMC, we use Memcached, Redis, and NStore, as well as example programs from PMDK, PMFS, NVM Direct, and NVM. We do not test strand persistency examples since no current NVM programs tried to implement it. In total, DeepMC reports 50 warnings for 8 programs we run it on, 43 of which are persistency bugs. From these, 24 are new, and the remaining 19 are those that we covered in our study. This shows the completeness of our checking rules on the bugs that we studied. From the 24 bugs, we confirm 18 with developers, and they break down as 8 model violations and 16 performance bugs. 18 of them were statically detected and 6 dynamically detected. We also find that the most common performance bug was the flushing of unmodified data, especially when certain conditions evaluate to be false, as was shown in the example. See the paper for more details on the new persistency bugs we find. We then evaluate the impact of DeepMC on performance. We first check the performance of the static component. We compile Memcached, Redis, NStore, first without and then with DeepMC. We see that static analysis introduces minimal compilation overhead. In the worst case, Redis sees 7.5 additional seconds of compilation, which is not very much. Next, we test the impact on performance of the dynamic analysis component. We run Memcached without and then with DeepMC and see minimal additional performance overhead, as little as 2%. Please see our paper for more thorough evaluation of DeepMC's performance. Finally, we discuss some limitations of DeepMC. First, we observe some false positives with DeepMC's static checker, since it cannot resolve all of the information statically, and some checks require dynamic information. Second, there are cases where developers are intentionally violating the model specifications. We extend DeepMC with a database for developers to register these warnings that should be ignored, so that developers do not see the same warnings reported over and over. Finally, the current checking rules were inspired by our study of NVM bugs and the model specifications. As these change and more bugs are found, these rules can be enriched. In summary, we begin by studying bugs in NVM programs. From these, we develop checking rules and a static and dynamic analysis tool, DeepMC, to detect them. We can show DeepMC's effectiveness by discovering 24 new persistency bugs in existing NVM programs. Thank you very much.